I'm not too loud, not too quiet.
All right, friends, we are ready to get started. So welcome Joe. He's our next speaker in the 2022 Senior Seminar Series, and he's going to be introduced by Deanna Donahue. Come on up.
Okay. Happy Wednesday, everybody. I am here to introduce Joe Heyman, and I have had the pleasure of knowing Joe for 3 years, I think. 4, maybe. I don't know.
Yeah,
I have
4.
to think about it. 4. I had to, yep, 4, all 4. I never remember. But then I really got to know you in analytical and particularly in instrumental. And I'm really excited for this talk today because it really comes from a deep passion, and it really is Joe's project. Joe did lots of other research and came to me this winter and was like, I care about open source. I care about education. And so Joe took this project on and has done really great things, and I've had such wonderful conversations, and it's really helped me think about what I believe with some of these technologies we use, and I hope that you all enjoy listening to this labor of love is what I'm going to call it. And welcome, Joe.
Thank you. So yes, I'm Joe, and or Joseph, officially. And my presentation today is going to be on open source instrumentation and STEM education, opening STEM education. And I undertook this project because it was something that really interested me personally. I had done other research. I'd worked with Stefan in his organic lab and his synthesis lab, and that was really interesting, but I was really brought to this through instrumental when we were talking about, we learned about sort of like electronics, and we broke apart the instruments that we used in lab, and I found that that was like such an educational experience that I wanted to do something similar, and it brought me to this, world of open source materials, which I'll get into more in the future. So yes, this is a project that I undertook, for the last 2 terms, and I found it to be really exciting, really interesting. So before I talk about the specifics of the presentation, I wanted to go more over the point of this presentation, sort of what I meant to get out of it and what I hope all of you can get out of it. And that's going to be talking about sort of like, what are open source materials? What are they as a whole? What, are the ways that they can be used in education specifically? And how does that look when we take something and integrate it into education, whether it's designed specifically for education or is adapted further for education? So just to go over an overview of what I'm going to be talking about, I'm going to start with a discussion of what open source materials are, what they look like, where they come from, how they started, how they're made, then go into how open source materials can specifically be designed and used in education, STEM education, and non-STEM education as well. I'll then be taking a look at an instrument which I designed using open source materials to be used in a Chem 116 lab, and the lab that I adapted to fit this instrument as well. And finally, looking at the future of this project that I went on, as well as the instrument itself, what the future of what the instrument can look like. So let's talk about what open source materials are. What does it mean for something to be open source? Well, the actual definition is that it's software materials which are designed to allow the user to download them for free, study them, make modifications to them, and redistribute them if they'd like. It's a lot about the modification and expansion of previously designed materials. This is largely seen in software, where a software will be developed and then released to large groups to be adapted and changed to fit specific needs. So open source began in the 1970s when this guy, Richard Stallman, who is a programmer at MIT, decided that he didn't like it when their printer wouldn't tell them that it was jammed. And so he hacked the printer and had it alert everybody who was trying to print something if the printer was jammed so that somebody could go and fix it. But then in the 80s, the MIT department got a new printer, and this printer had proprietary source code, so he was no longer able to access it. And he thought to himself, well, this doesn't make any sense. I should be able to change it if I need it to do something different that nobody else needs, like alert me when there's a printer jam. And so he went off, and he started sort of the open source movement. And it has evolved now today to be something that large tech communities will use as ways to adapt their own resources to fit specific needs and develop them into a wide range of technologies. So places like IBM and Sun Microsystems have spent a lot of money and time developing open source equipment that's used by NASA and other large scale and even small scale industries because of how widely available and accessible stuff like this is. And this tree details just a few of the different programs that you might find that happen to be open source. You might be familiar with something like Blender if you're into 3D art. That's an open source material that can be downloaded for free and modified, as well as something like Linux, which is an operating system, much like Windows or iOS, and that is what's used by NASA and other large industries for their projects. So how are open source materials made? What starts an open source material on its journey to becoming something that we can use today? Well, it starts with someone or a group of someones working together to solve a specific problem. And they always set out with the initial goal of it being an open source material. They set out with the goal of it being something that is not proprietary and you don't have to pay to have access to specifically. So they'll develop an initial code, an initial software, which can then be shared with a larger group of people, a larger group of developers who will take this project and they'll modify it themselves. They'll develop it into something new. They'll develop it into something that's more refined. And over time, it gets modified by people outside of this initial group, the initial people that it's shared with, to individuals and companies all around, to the point that it becomes something that is matured to the point that it can be used by someone without experience in development, without any of the knowledge that it takes to make something like this. You can still use it effectively and specifically to suit your needs. And what are those needs? How are open source materials used? Well, they are used in a variety of different ways in a lot of different subsets of action. Specifically, some examples, it can be used in something like community involvement, where we have large groups of people who don't have a lot of experience in development or coding or anything, who can come together using this open source technology, like the Louisiana Bucket Brigade, who used this EPA-approved bucket. It is literally a bucket, and are able to test the air quality of their neighborhoods very easily and cheaply. They use this bucket, is like $75, but it's the same technology as this $2,000 technology, and it works just as well. They've been using the same design since 1995 to test the air quality of these communities by factories and other sort of like affected communities. They've been able to test for things like benzene in the air, for things, high levels of pollutants. But it's not just used in community involvement. It's also used professionally in research, like is found with the Jupyter program. These are a set of interactive web tools such as the computational notebook, the Jupyter notebook, which is commonly used in computational science throughout different subsets, throughout different disciplines within science. Its open source nature allows it to be modified to the point where it can be accessible to anybody who needs it. So the computational notebook itself is sort of a digital lab notebook, and oftentimes this is where you'd write about the code that you're writing in. So you need something that can fit to the code of whatever language that you're working in. And people have been able to design Jupyter notebooks to fit to dozens of different programming languages, which is great because the field of programming is always changing. It's relatively new. New languages are always being developed and modified. So to have something that you can write about them with specifically is important. And since 2018, there have been over 2 million Jupyter notebooks published, and even more so as we continue. But it's also used in education. This is a completely different realm compared to the first two in that it's used to build skills from the ground up. Like, for example, with coding. Oftentimes it's used with coding. Something like the Snap program, which is a coding language designed for someone who has never taken a class in coding before. It has pieces that you snap together to create the code. And because it's open source, you can change those pieces to be fitting to what you want to be able to do if you are instructing others in it. There are also guided electronics and coding projects, such as those found from like Mozilla Firefox. They put together a whole bunch of these coding projects that can be taken on by someone without any experience in electronics or coding, and they can build a functioning project that helps them to be educated in the field. And then also completely outside of this, something like a learning management tool like Moodle and Canvas, which I'm sure we're all very familiar with. These are also examples of how something like an open source website can be used in education. They allow teachers to adapt their page, their landing page for their course to fit their specific needs. I think currently all of my teachers use Canvas in a completely different way to how they are relating the material that we're learning in the class. But if we're looking specifically at education, we can also look about how open source materials benefit education. This is the focus of my project, and I found that we can focus on two specific areas of how open source materials are a benefit to education. We look at how they can be a benefit to hands-on activities such as labs, and how they can sort of help to bridge the gap in terms of equity. They can help sort of bring new materials into areas where they initially wouldn't have been available. So we're going to start with hands-on activity. We're going to look at why hands-on activities are important, why labs are important. And it feels kind of silly to bring this up in a room of educators and students who have all taken labs and feel, perhaps that they are incredibly useful. But it's important nonetheless to look at the learning goals of what makes a in-person lab or a hands-on lab important. So these are all learning goals that come from the American Chemical Society and their analysis of the effect of hands-on labs and how they can benefit education. They work to develop our problem-solving skills. They help you to solve problems outside of what we specifically see in class. You can learn how to adapt the skills that you've previously learned into an unknown environment. They also encourage group collaboration. A lot of science involves group collaboration. Most of what we do involves working in groups. So being able to develop those skills of how to work in a group is incredibly important and is something that comes out of these lab experiences. They also help to strengthen the understanding of materials that are learned in classes. They are an added section which can take the stuff that we learn in lecture and contextualize it within the source of what we're doing in lab to sort of help to strengthen those educational points that we learn from the lecture itself. And finally, it helps to teach laboratory skills. These are incredibly important, as we've all known in chemistry, to specifically learning how to use different lab instruments. This is stuff that's going to be incredibly important if we want to continue our journey into chemistry, and is something that is important even if you're not looking to continue your journey into chemistry, because of how it helps us in understanding laboratory skills. So hands-on activities. These are the 4 points that I just brought up. How do open source materials specifically help to strengthen how these learning goals are met within the context of a lab? So for looking at how they help to develop problem-solving skills, the open-ended sort of nature of open source materials allows you to have complete creative control of how a lab is designed and how a lab is brought about. This is, of course, not always going to be what you're looking for if you want someone to do a very specific thing. But if you're looking to bolster how people can attack a problem specifically, having a material which doesn't have one specific right answer allows you to come to that conclusion a variety of ways will really strengthen how you can develop these problem-solving skills, give people the creative control to solve the problems. For encouraging group collaboration, well, all of open source is designed around group collaboration. No open source material is made by one person. It's made through a group of people, and it's reflected then with how it can be used. You can design an open source material to be used independently or to be used specifically by a group, and so you can help to facilitate these group activities, these group learning sections to all work together. And when we're talking about strengthening the understanding of materials, the open source nature allows you to specify which parts of a lab you deem are the most important to understanding the materials that you're going over in lecture. For my my instrument that I designed specifically, it cuts out a lot of sort of the busyness of the initial lab that it was written around and focuses more on the chemistry that's going on. So you can specify specifically what you want students to be looking at more importantly, more intently, without distracting them with sort of other aspects of the lab that might take up more time or generally be a little more confusing. And for teaching laboratory skills, well, the open source materials allow full analysis of the instrument. They allow you to break it down to its most rudimentary parts and build it back up again in a way where you understand completely what it is that the instrument is trying to do. You can understand what data the instrument takes, how it processes it, and then what that translates to when you're looking at the graph or you're looking at the data that's presented. But at the beginning, I brought up equity, and I do want to mention this a little bit as going on, is how sort of equity comes into the discussion of open source materials. You have some things to talk about when we're looking at like equity in education. We think about something such as the cost of materials, whether that's restrictive. We want to look at whether certain schools are not able to get the same materials as other schools and how that affects the experience of the students. Also, how difficult it is to acquire materials. Especially when we're thinking about chemistry, it can be incredibly difficult to get the materials that you need to carry out a certain lab. And so, how does that impact the education as well? Meeting the specific needs of the students, looking at, not every student is going to have the exact same needs, so you want to have something that's adaptable to what they specifically want to get out and can get out of a lab experience. And lack of expertise is another one. This comes down to sort of the nature of the class itself, the nature of the educators itself. In some districts, you might have one teacher that's teaching multiple levels of science, and they don't have specific expertise in one level as much as they might have in another. So let's look at how open source can be responsive to these challenges that are brought up as well. So for cost, open source materials are entirely free to download. They're entirely free to adapt and change because there's no proprietary aspects to them. If you want to use a physical instrument that goes along with the software as well, then it does have some price to it, of course. But when you're building the instrument itself, oftentimes, like we saw with the Louisiana Bucket Brigade, the cost comes dramatically down. In terms of difficulty to acquire materials, open source materials are free to download all over the internet. They can be taken directly from the internet without any hoops to jump through. For meeting the specific needs of the students, I think this is one of the areas where open source excels because they have a complete adaptable design. Everything about the nature of these programs allows you to make small changes, allows everyone to make small changes to fit the specific needs of what you're trying to get out of the software or equipment. And for lack of expertise, open source materials like we saw with the Snap programming language, they have levels for everybody in terms of all levels of experience. They can teach you from the bottom up all the way to more advanced materials. So now that I've introduced what open source is, the challenges that it addresses, and how it responds to a lab environment, I can talk more about what it is specifically that I did. So as part of this project, I went out to try and design a instrument to be used in an introductory lab, specifically a Chem 116 thermodynamics lab. So I designed this calorimeter. It's a fairly simple calorimeter. It takes temperature, much like a calorimeter would, and it is an insulation thing, much like a calorimeter is, and it stirs. Very exciting things. And what I set out to do with this project was to utilize open source materials to build this calorimeter. This comes from both an open source parts list and design aspect, as well as the software specifically. So I was able to find open source software and adapt it to my specific needs. And then as a final step, I wanted to have a lab that went along with this instrument, a lab that could be designed around something like this. So when I set out to build this, I had to come up with some goals in mind when I was developing the lab and the instrumentation. Starting with the educational goals, what I wanted people to get out of the experience. Well, I wanted to encourage critical thinking and problem solving, like we'd talked about before, with these core aspects of what is a hands-on lab. So I wanted to encourage people to think critically within the context of the lab, and have the option for problem solving in the context of the instrument specifically. I wanted it to be accessible, but yet still moderately frustrating, not something that's just a plug-and-play design. It still has you working to understand it, but is still not having the core difficulty within the lab being just trying to get the instrument to work. So having something that's still a little bit frustrating makes it an educational experience all on its own. And then, of course, having it be adaptable, having it be able to change and modify its having it to be able to be changed and modified to fit the specific needs of students. Then, of course, there were design requirements as well. It needed to be something that was low cost, which was a core aspect of this project as a whole, having something that could be made for a lower expense than the proprietary technology that would do the exact same thing. Had to be user-friendly, so like I said, moderately frustrating, but that's not the challenge that you're trying to overcome in the lab. It's supposed to be still focused on the lab itself. The design was meant to be something that was more modular to promote further improvement of the design itself, and also have a low complexity to promote that further improvement of the design itself. As it stands right now, it's incredibly basic. It can be easily modified to fit any sort of specific need that you'd like out of the instrument itself. So when I was designing this, I had come up with the educational goals, but I needed a way to control it. I needed a brain for the entire instrument. And so I came to Arduino. Now, Arduino itself is a hardware and software company, and all of their technology and materials that they have are open source, relatively free to the public. Their materials specifically, not always free to the public, but their coding specifically allows you to access it and learn from it as you're going through. I used the Arduino Uno specifically as a small computer, a microcontroller, to download the code that I adapted onto and run the entire instrument itself. The Arduino I picked is because it is relatively inexpensive, about under $30, depending on where you're buying it from, and is an incredibly adaptable little piece of equipment. Highly customizable and user-friendly, because you don't have to solder anything to get it to connect to what you want it to connect to. And it can be powered either from your computer or from a DC circuit. In general, it has a lot of very accessible options, as well as the fact that Arduino specifically are designed with education in mind. This being a core aspect of the project itself, I wanted to make sure that education was still met throughout this whole thing. So Arduinos, although there are other microcontrollers that are available, Arduinos are the ones that are most often designed to be used by people without a lot of experience, which is also me, which comes into why I picked a calorimeter. So I needed to think of an instrument that would be used in an introductory lab. And I also needed one that wasn't going to be too difficult to build, because I have basically zero experience building instruments and coding and with electronics. So a calorimeter seems like a great option, because it is basically just a thermometer. And of course, an insulating chamber and a mixer and all of that. But at its core aspect, it is incredibly simple, as well as it being an incredibly useful instrument in terms of these introductory labs. With these thermodynamics labs, you can get a lot out of it. Talking about enthalpy, entropy, you can get a lot of information out of the labs that you undergo with just a simple calorimeter. So now that I'd known that I wanted to go to a calorimeter, I came to looking for sources to try and pull a design from. And so it led me to this paper that was published in the Journal of Chemical Education, which became kind of the core base for this project as a whole and what it meant. They too set out to design an accessible and low-cost calorimeter, which would be used in a lab to fit these specific needs that are presented. Talking about these concept building, problem resolution, bridging the gap, and trying to develop an accessible lab. Unfortunately, this design did not work out that well. The materials for it worked out great, but the coding specifically ran into some issues, as the code that they had written used some outdated libraries, which is basically what is needed in order for the Arduino code to communicate with the thermometer itself. So because they had outdated libraries that they were using, I wasn't able to get their sections of the code to work. And that meant that none of it worked, which was not that fun to realize, and led me to another attempt. So I led to another attempt which modified some code from this website, microcontrollerprojects.com, which posts freely available open source code for anyone to use and adapt. And so that's exactly what I did. I took a code that specifically just read a thermometer and displayed it on a screen, and was able to adapt that specifically to fit the needs of the calorimeter that I had. This code was much more simpler, and it had a less complicated hardware setup when all things were put together, which of course leads to this, that it's more easily modifiable in the future. You don't have to think about as many components that it has when you're trying to add more pieces to it later. To show you how much simpler this new design is compared to the old one, here's a side-by-side comparison. The first design in the box, and it has two independent power sources, which is beneficial for the how portable it is, but really complicates the wiring of everything. They also had significantly more wires that were just not needed. And this meant that if something went wrong as you were going through it, it created a whole issue of trying to find what was going wrong within the instrument, which is much easier to solve in the second design. This is just two pieces. It's a thermometer that's being read by the Arduino and a motor that is being powered by the Arduino. And we can get into now more of how this calorimeter specifically works. So it starts, when you're doing a lab, it starts in the insulation chamber. You'd add what you needed to add to it, mix it together using the motor, and the thermometer takes temperature data. Once the thermometer has taken temperature data, it goes to the breadboard, the wiring board, where it will be transmitted to the Arduino and the LCD shield, the liquid crystal display. That's what this is above the Arduino. It fits perfectly over the top of it, plugs right in, and allows you to display in real time the thermometer's readings. You can adapt this display to be whatever you need it to be. I currently have it as Celsius and Fahrenheit, but you can also have it display Kelvin, or you could have it display the time as you're taking the experiments. In general, it's incredibly adaptable to whatever you want it to display. I also have it give you a little welcome message when you turn it on, which I personally think is fun. And then it ends up at the computer. And at the computer, you basically just get very simple data. You get a line of numbers, which are the temperature. You just get the temperature every single time the temperature is taken, and you also get a graph, which will plot the point to every time the temperature is taken. These are not two data sets from the same data set, from the same temperature reading. That is why they don't match up entirely. But you get very simple data out of it. And the point is that you can take this and then move it into Excel, where you can analyze it further. And that's where more of the lab aspect comes in. But if we're going more in depth on how the instrument works specifically, we can look at how the Arduino is connected to the thermometer. It's a very basic circuit. It's just 3 wires. And so we had 3 goals when assembling this circuit. The first, of course, is supplying power to the thermometer, very important if you'd like the thermometer to work. The second is grounding the thermometer, also very important if you don't want to burn out any of your electronics or get electrocuted. I highly recommend it. And the third is to collect data from the thermometer. You want to be able to, of course, collect data from the thermometer. That's the most important part of it when you're trying to assemble this instrument. And so this is the construction. And so when we're supplying power to the thermometer, you have this structure here, which is simply the Arduino powering the one of the lines of this breadboard here going directly to the thermometer. And then if we're grounding the thermometer, it's the same thing, except on the other side. You have a grounding port connecting to the wires here, which connect to the thermometer. And then the data is carried through just through one wire directly to a data port, which allows you to take signals from the thermometer and interpret it in the LCD screen and on the plot and the table. The whole wiring setup is incredibly simple, like I said. So you have the wiring that was put together for the thermometer, and then you also have the wiring that is put together for the motor. This is a simple setup. It just connects the motor directly to the Arduino. Similarly to how it is connected with the thermometer, you just have it connecting over on this section of the breadboard. And then the only other real point to make is this variable resistor that is present to allow you to control the speed of the motor. Something to point out is that this is not the most optimal setup for the motor. Right now, since the motor and the thermometer are connected to the same power source, there's an issue where the motor is going to be drawing power at inconsistent variables as it goes throughout its rotation, and that's going to cause noise within the thermometer's data. This is not something that I've noticed, but it is something that I'd like to correct. I originally had this wired this way because I was out of batteries, and so I did not have another way to power the motor. So now we can talk about the code. The code is boring to look at, so I put this picture of my dog here that you can look at as I talk you through the goals of the code. You'll be able to look at the code again later, but this is what I wanted to put for this section. So I had 4 goals when looking at the code. I wanted to be able to read the thermometer, of course, very important when we want to take temperature data, present that data on the LCD shield so that you could monitor it in real time, and then also allow you to graph the data separately so that you can take the data from, you can just copy the data directly into Excel without having to write it down and then enter it into Excel by hand. It just smoothens the process much quicker. And then also to have it allow adjustment by students, allow them to adjust specific parameters themselves. So the code here, this is all the code that's present. It's not that long. It's incredibly short when it comes to code, and it does very simple things. The code that I added specifically is outlined here. You have a section here which just allows you to initialize the temperature taking by pressing a key. The original code just had it automatically taking temperature, and this allows you to control when you start and stop the experiment. And it has this little welcome message, which just says welcome. It also has a section which allows you to start and stop the data taking over here because it's required by the coding language, and then another section that allows you to print out the data on the monitor for the data and for the table and the graph. And then also this time delay section, which allows you to change how often the calorimeter is taking data. When a student is going to be interacting with this code, they don't need to care about any of these lines except for one. They only need to care about this one delay line because that's where they can change how often they're taking data. Currently, it's set up to take data every 15 seconds. But by the nature of it, you can take data down to fractions of a second all the way up to minutes, depending on what kind of experiment you're running and how often you need to have data for it. So I've brought up now how a student would interact with the code, but how would the calorimeter actually be used in lab? So the lab activity itself would just be to have students take a series of data points from using this calorimeter to better understand how dissolving salt in water, the thermodynamics of dissolving salt in water. The learning objectives for this lab were to allow people to understand better sort of, enthalpy, Gibbs energy, criterion for spontaneous processes, the things that we cover in a thermodynamics lecture and then want to see covered in a thermodynamics lab. The lab itself, the setup is fairly simple. You have the calorimeter hooked up to the LCD shield, hooked up to the computer, like I walked through before. Here I have a wonderful student demonstrating how a lab setup might look. And as they go through lab, there are 3 procedures that they'll undergo. They'll calibrate the calorimeter, they'll determine the enthalpy of potassium nitrate, KNO3, and then they'll find the change in enthalpy and entropy using equilibrium. That can be determined by testing multiple concentrations of KNO3 using the calorimeter. So do we need to calibrate it? Absolutely, we need to calibrate it. Every time you're using a calorimeter, it's important to calibrate it because every calorimeter is slightly different. So finding that calorimetry constant is important for determining the effect that running a reaction in this calorimeter is going to have on the data that's taken. The procedure for this is very simple. It's 50 milliliters of hot water monitored every 15 seconds for 5 minutes to watch how it cools over time. This is a cooling curve taken from the calorimeter's data, and it shows that you do lose some of that heat over time, only a few degrees over the course of the 5 minutes, which is nice to see. And we can see that this is what we want it to look like when we compare it to an example cooling curve that was taken from the initial Journal of Chemical Education article that I had looked at. And shows you how you want this like slight decrease. There's no surprises that we found. Great to see. And the specific heat that we found, this calorimetry constant, that's the amount of heat energy that we're losing into the calorimeter and how much energy specifically it's taking, it's leaching from the environment itself that we're running the experiment in. So now that it's calibrated, we can look more into the dissociation reaction that I was talking about. What we can learn from the dissociation of salt in this instrument, the dissociation of salt throughout this lab. So we're looking at the dissociation of KNO3 into K plus and NO3 minus. The procedure is fairly simple. Again, we use 5 grams of this potassium nitrate in 50 milliliters of room temperature water. We dissolve it in the water and monitor it over the course of time as the water decreases in temperature. And we can track that decrease in temperature to find the overall change in enthalpy for the reaction. And what we get from that is this change in temperature due to dissociation, a slight decrease over the course of that 5 minutes that we see from the breakup of that KNO bond. So we're decreasing down, this was about to 18 degrees Celsius. And we find the enthalpy of reaction, for this one specifically, the change in enthalpy, about 23.45 kilojoules per mole. When we compare that to the literature value, we are off by a rather significant margin. So this is not really an issue when we're thinking about the type of lab that we're running here, because while, of course, you'd like to get incredibly accurate data, we're seeing data that reflects what the nature of the lab still is. So you can learn about the relationship without necessarily getting the perfect data that you initially sought for. But there's one final procedure that we're going to be looking at, and that is the procedure for finding the change in enthalpy and entropy of the KNO3 dissociation. So it's that same dissociation reaction before, only this time we'll be dissolving a series of concentrations in the water, in water itself. This one is not done specifically through the calorimeter. It's done by dissolving 8 grams, then 6, 4, and 2 grams of water, or of the KNO3 into hot water and monitoring the temperature at the point when it starts to crash out, the equilibrium point. So this data is then monitored, and we can use this equation, a complex equation that doesn't need to be incredibly explained right now for the purposes of this presentation, to find the things that we're looking for, this change in enthalpy and change in entropy. If you'd like to learn more about this equation, I recommend taking Allison's advanced thermodynamics class. You go over this a lot. And what we're able to do is analyze this data using this linearized equation. And we can solve for the change in enthalpy and entropy in this way. And the data that we get from this shows like this. It's a line. It's adjusted to be a line and allows us to get the change in enthalpy, the change in entropy, which we can compare to the literature. So this is a different value for change in entropy, or enthalpy, as I'm sure you'll notice, and that's due to just how the experiment is run. This one's not done in the calorimeter, so we don't adjust for the calorimeter constant. It causes a little bit of change in the data that we'd find. And again, we see that the change in entropy is different from the literature value for the change in entropy. And like I said before, this is not something you necessarily want, but it's not something that is causing a great disservice to the lab itself. So there are, of course, ways that this instrument compares to the current instrument that is being used in the lab. We can compare it based on 2 options, the quality of data and the ease of use. So the quality of data itself is pretty much exactly the same. And that's because we're using the same calorimeter, or we're using the same insulating container. The insulating container is exactly the same as the one that was used in the initial lab, so we're going to be getting that same calorimeter constant, essentially, and the same quality of data. Ease of use, though, is what dramatically increases. The initial lab involved students monitoring a stopwatch, stirring the mixture, and taking data every 15 seconds by hand. The new calorimeter does this all independently. The new calorimeter stirs, takes data, and in a sense is timing itself throughout the entirety of the reaction. So you don't need to be doing these things independently. You get a more consistent mixture than you would have if someone was just mixing by hand. And you don't have to worry about people missing the clock in terms of trying to take data every 15 seconds. But of course, how can this be improved? There are always ways that we can improve this. This is the nature of open source technology, is that it is meant to be improved. The first one is, of course, designing a permanent design for this. Right now, it is still unsoldered on a breadboard, and the wires can just kind of fall out. So not something you'd like when you're trying to use it in a lab, and something that can be improved fairly simply by adapting the wiring to a printed PCB or soldered PCB, much like the breadboard, only more permanent. The second would be waterproofing. Currently, it's not waterproof, which is not something you'd like in an instrument that deals with water. I have spilled water on it personally, and luckily it didn't damage anything, but it's not something you'd really want to be worrying about in the lab itself. The third one, and this one is more crucial to how the ease of use can be sort of benefited, and that's how direct data collection could be brought into Excel without having you to do a separate task entirely. You could take data that would be automatically turned into a plot in Excel, and you could even have it processed automatically as well if you'd like. Not as great for the educational aspect of the lab, but certainly great if you're trying to do something quickly and easily. And lastly, and honestly the most important personally, is the accessibility functions of it. Because of its simple design and its modular design, you can add a wide range of accessibility functions to an instrument like this so that you don't have any sort of unnecessary challenges when trying to have it be adapted to anyone, for anyone to be using it. It can be incredibly useful to anyone who's trying to use it. And then the last point I wanted to make kind of detracts from the overall discussion, but is based on everything that I've done. And that is this process that I underwent as a class itself. I felt that my experience personally would benefit from sort of a classroom attempt, a classroom design, wherein students would be able to choose a lab themselves which they'd like to design or adapt to fit open source materials, and where they would also research how groups have attempted to answer the questions that are answered in this lab through open source materials. They design and prototype an instrument themselves, which would be able to be used in an introductory lab like the one that I've designed, and also design a lab to go with it and for introductory students to use. I found that the process of trying to go back and create an introductory lab after 4 years of chemistry was much more challenging than I anticipated, just because it's after you've learned all of these things, you don't really think about how to explain them to someone who hasn't learned them at all before. A lot of what we cover gets covered over and over again, and so you understand the concepts without necessarily being able to explain them on their most basic levels. And so when trying to design this thermodynamics lab, I had just come out of thermodynamic chemistry, and so I'd had, in my head, had all of these notions from this advanced class that now had to be taken back to the assumptions that we make from introductory chemistry and the simplified versions of equations that we use in introductory chemistry. And that's my presentation. I'd like to thank Deanna for advising me throughout this whole process, Allison for giving me the original idea to try and tackle an educational lab. Thank you for that. Eder and Jesse for being the peer reviews from my 680 class, and Ethan Wilmus, who was the student, my friend, who took the picture with me in the lab, pretending to use the instrument. Thank you.
All right, Joe is ready to take questions.
I was curious about the visualization of your setup made sense, but how are you physically measuring the temperature in the calorimeter, if that makes sense?
Like how is the thermometer, what's the setup of the thermometer in the calorimeter? Or?
Yeah, like just the physical setup of because I saw it makes sense to have the motor to stir.
Yeah.
Just how are you?
So it's, this is the stirrer here, and this is the thermometer here. They go in the same port. They do not touch when they're in the calorimeter, luckily, which is nice because then you're not damaging the thermometer itself or causing odd data. It's just a submersible thermometer probe at the end of a long wire, is what it is.
James?
I know that for the stirring process, you can like change the torques of the motor and change the speed. Did you like do it as a constant speed or like the variation? Or?
Yeah, so the reason for the variable speed is that you can change how much things are being mixed in, and you can set it at a constant speed while it's doing that, if that answers your question.
Allison?
Assuming that there are other non-questions. Okay. So yay thermo. This is the win. But in the KNO3, I think it's potassium.
Yeah.
Yep. You start with hot water, 5 mils of hot water with the added salt. Is there a reason that you're starting with hot and not room temperature?
Right, so starting at the point where it's completely dissolved and then bringing it back down to the point where,
Got it.
yeah, so, I guess that might have not been entirely clear in my
I'm
initial.
probably not paying attention. And then, so my other question about that is, not to get the picture up, one of the hardest parts of calorimetry is heat loss to the surroundings, and that curve that you saw showed of your control, I guess, of the water, where you can see that that wasn't changing that much in temperature.
Mm-hmm.
But when you do the different concentrations, so I assume how do the students get the stuff in? When is the initial start of the data collection?
Right, so,
Makes sense.
yeah, so that experiment is done in a test tube with the thermometer in it, not initially done in the calorimeter,
Oh, okay.
so that you can watch it as it recrystallizes, because this setup does not allow you to look and see when crystals initially start to form.
I'm thinking about how to incorporate this into class. So go team. Thank you.
Well, I'd start with waterproofing it, personally.
Yes, over here.
So I'm not necessarily skeptical of the fact that these open source softwares are free for the average chemistry enthusiast. But what keeps them free? Like, what is the economic incentive to provide a free product? Is there funding? Are there shareholders?
Yeah, so what keeps them free specifically is that it's licensed as open source. So it prevents it from becoming proprietary technology itself. And then the reason for this, I guess, I don't really know specifically why it is economically viable. I don't know a lot about economics. But these large-scale tech firms are able to use these, if they can use these technologies to the point that they're useful to them without having to spend any money, then it's useful for others as well. And also because of grants and stuff like that. There are groups which seek grant money to develop stuff like this specifically for education or research to give this free resource to anybody who needs it.
Yes, Mike?
What's to prevent somebody from putting malicious code in?
Well, the malicious code.
I assume you're downloading the code,
Yeah,
but then you write a package and you say you distribute it to others.
yeah. So what's to prevent someone from downloading malicious code onto your
Yeah, you
computer?
could put
Yeah,
some
so that's
code
part
in
of.
there.
Yeah. So part of that comes from the companies that distribute these open source technologies. They can be reliable themselves. Of course, that doesn't completely answer the question of you could still download malicious code through these open source softwares, which I guess is especially an issue if you don't really know the software itself. But a lot of these softwares and a lot of the softwares that are used by people who don't have a lot of experience in coding have been refined to the point where it's essentially a product, just a product you don't have to pay for. And so I guess for one thing, it's easy to trace who made that addition to the code. So you can always find who downloaded this malicious software onto your computer. But as well, they usually come from reputable sources. They do come from reputable sources. Like I guess I've brought it up before, but the Snap program itself, it's an entirely own program that comes from a company that's dependent on making these free and available sources for students.
I have a question. Convince me I'm wrong. The activity was more hands-on before you added the Arduino, because they had to do all the stirring themselves.
Right, so it does involve more hands before you added the Arduino. What the point of the Arduino and the general sort of ease of use changes is that it takes away the difficulties that come from just trying to stir it and monitor sort of things that detract from the lab experience itself. If you're trying to sort of guide the students through understanding this thermochemistry lab, you don't want the focus to be trying to stir something while also writing down the temperature at the right time. Unless that's the specific goal that you'd like, in which case you are able to do so.
It just doesn't sound as fun to just hit go and sit for 5 minutes while it takes the temperature.
Well, yeah, but did I mention it says welcome when you turn it on?
Now that is fun. Other questions for Joe? No one on Zoom has questions. In person? All right, let's thank our speaker again. Join us on Friday for one more senior experience talk this week at 3:10. It was moved.
Was yours? Did you?
No, these are mine.
I have a random chemistry question.